We now turn to measurement of cosmological parameters, the first one of which is Hubble constant, or Hubble parameter. It sets both the spatial and temporal scales for the whole universe. In a given cosmological model, specified by values of different omegas, or little w as well, all distances and all times scale linearly with Hubble's constant, and thus its importance. So the inverse of the Hubble constant is the characteristic time unit of cosmology, the Hubble time. Multiplied by the speed of light, it gives Hubble length, which is commensurate with the size of the observable universe. Note that Hubble's constant is independent of all other cosmological parameters. We have this neat separation between Hubble constant that sets the scale and all other parameters that describe the qualitative behavior of the universe. So distances to anything, galaxies, quasars, anything in cosmology, scale with Hubble's constant, and thus its importance. Moreover, physical parameters of objects like galaxies or anything else, such as their total luminosity or their masses or physical sizes, all scale with the distance, with the appropriate power. And in order to understand these objects better, and how they form and how they evolve, we need distances to them. However, measuring the distances in cosmology is a very difficult thing to do, because galaxies are very far away. And in fact, the only distances in astronomy that are measured cleanly without recourse to any models or statistics are trigonometric parallaxes to stars. Everything else requires some sort of physical modeling or assumptions or statistics. Thus, we have a concept of the distance ladder, which means that we first measure distances to objects where we're sure how to do it, such as nearby stars. Then we use that to calibrate distances to some objects further away, star clusters say, and so on and so on. So we calibrated distance indicators relative to each other. And this is what's known as the distance ladder. Locally, those would be various stellar types of indicators, say based on pulsating stars or star clusters and things like that. Then properties of nearby galaxies used in their scaling relations, and so on, until we reach what's called pure Hubble flow, where only the recession velocities matter. And that is where the expansion of the universe, unperturbed by local non-uniformities, really sets in. Now, the age of the universe can be actually estimated independent of Hubble's constant. The look-back times to objects cannot, but the total age of the universe can. We can, for example, estimate ages of stars or clusters or chemical elements, and that gives a lower limit to the age of the universe, independent of any measurements of distances. This is a hard thing to do, and thus measurements of Hubble constant have somewhat disreputable history. Hubble's own estimate of it was an order of magnitude off from what we know today is more or less the correct value. And through the history, people always thought they knew it to about 10% accuracy, even though its value changed by a whole order of magnitude. The reason for this is that they didn't really account properly for errors of measurement, and especially for the systematic errors. So for example, when Hubble first measured value of Hubble's constant, 1 over that was a couple billion years. And already then, people knew that there were rocks on planet Earth that are 3 or 4 billion years old. So planet Earth was older than the universe, and that was a problem. Ever since then, the value of the Hubble constant was revised, usually downward. The first major revision was due to Walter Baade, who recognized that there are really two very different kinds of pulsating stars, one of which is confused for the other. And he came up with the concept of stellar populations that immediately halved the value of Hubble's constant. Then improved measurements pushed it further down and down. And in the 1970s, it got down to the range of between roughly 50 and 100 kilometers per second per megaparsec. There were two prominent schools of thought on this. One, led by Alan Sandage, the disciple of Hubble, pushed for the lower values, around 50 kilometers per second per megaparsec. The other one, led by Gerardo Oculer and his collaborators in Texas and elsewhere, pushed for twice that much, about 100 kilometers per second per megaparsec. And the two just could not get into an agreement. The reasons for this were they made different assumptions and used different calibrations, and things went like that until 1980s. But even in the modern days, the spread continued. People started being more careful about the error bars, and yet still the actual spread of quoted values in the literature was always larger than the measurement error bars. That persisted until roughly 1990s. There are two kinds of methods to measure distances. There are methods that ostensibly give absolute distances to particular kind of objects, like trigonometric parallax for stars, or using physical models to derive distances to supernovae or clusters of galaxies. Parallax is the only safe one. The geometry is well understood and there are no problems. However, we cannot measure parallaxes of stars more than about kiloparsec from us now, well within inside of our own galaxy. There is so-called moving cluster method, but that relies on statistics and certain assumptions. There is so-called Bade-Wesselink method that uses pulsating stars. That too makes assumptions about stellar atmospheres and things like that. Very similar to it is so-called expanding photosphere method for supernovae. There one also has to make some non-trivial assumptions about physics of what's really an exploding star. Pushing further in the Hubble flow, there are two important methods. One is based on so-called Sinaev-Zeldovich effect, which measures distances to clusters of galaxies using observations of cosmic microwave background and of the X-ray emission from clusters. We will talk about those in more detail. And the other one is using gravitational lens time delays. We will also address that one in due time. The other kind of distance indicators are secondary ones, which require calibration from somewhere else. They can be used to measure relative distances, say fainter objects must be further away, but their zero point has to be obtained from something else. And there are many of those, both using stars and galaxies, and we will address them all. So here is schematically what the distance ladder is like. Each method operates in a certain range of plausible distances. Hopefully it overlaps, in part at least, with another method which then can reach deeper and so on. That is what we call the distance ladder. Nearest to us, trigonometric parallaxes can be used to measure distances. Proper motions of stars can also be used, but in a statistical sense. Then we can measure distances to some of the nearby star clusters and use properties of star clusters to measure distances to even more distant ones. In particular, this leads to measurement of distances to pulsating stars, Cepheids and so-called RR Lyrae stars, which are key step in the measurements of the Hubble constant. But notice that several steps precede them. With those, we can measure distances to a number of nearby galaxies, and then we can calibrate distance indicator relations for galaxies themselves. Those are correlations between two quantities, one of which does not depend on distance, say rotational speed of a galaxy, and the other one of which does, like luminosity. So these important distance relations can be used to measure distances to galaxies far away, but they have to be calibrated locally with something else. Then supernovae come in, and those are currently favorite ways of measuring distances in cosmology from near to far. We will cover them in some detail. Once we go beyond the regime where it's easy to do galaxy distance indicators, two other methods come in on really cosmological scales, the Sinaev-Zeldovich effect and the gravitational lensing. In principle, they do not depend on the distance ladder. However, they are model dependent, and therefore previous calibrations are important as a check. So here is a schematic flowchart. It's not there to confuse you, it's just to show you a little bit how complex the network of measurements has to be with mutual checks to find out how far things are in the universe. It starts with nearest stars and goes all the way to supernovae and truly cosmological scale. Well, that's it for now. Next time we will actually talk about stellar distance indicators.